Hello everyone and welcome to this new meeting of Ithaca Fest. I think the last one before the summer. It's nice to have you here, and today we will have a day mostly around categorical logic. And the first speaker of the day is Matteo Spadetto, and the title of the talk is A Conservativity Proof Strategy via Two-Category Theory. Matteo, please take the stage.
Thank you, Ivan. Thank you for the presentation and for the invitation. The content of the talk will be the following. I will start by recalling how to prove conservativity between type theories via a semantic approach. Since we need semantics, I will say a few things about the categorical semantics of dependent type theory, especially focusing on path categories and display map to categories. And finally, I will use these tools to give a proof of a conservativity result. All right, let us briefly review Hoffman's strategy to prove conservativity. Suppose that you have a theory T2 that extends another theory T1, and the idea is that you would like to prove that such an extension is conservative. What do you do in this case? You try to build a model M of T2, that in particular it will also be a model of T1, such that the interpretation of T1 in M is surjective over terms of reachable types, a sort of fullness condition of the functor K. I will illustrate it by explicitly proving conservativity under such hypothesis. Suppose that you have a type T of T1, and suppose that its interpretation, IT in T2, is inhabited, so we have a proof T of a capital T in T2. And we would like to sort of lift this proof to T1. Then what do? We interpret this judgment via J into M to obtain a section of the display map interpreting the type T, because this is how terms are interpreted in a model, sections of display maps. Now I can write K in place of Ji, and because of this fullness condition that I was mentioning, we can lift Jt to T1, so obtaining a term T prime of the term T. So after all, from the inhabitability, from the proof, from the fact that T2 is able to prove T, we deduce that even T1 is able to prove T. So in other words, T2 doesn't increase the proof strength of T1, as long as we talk about statements that we can phrase, that we can express in T1. So for today, T1 is ATT, Martin-Löf type theory with computation axioms, and T2 is ITT, so ordinary intensional Martin-Löf type theory. We are interested in proving that ITT is conservative over ATT. I'm not proving this today. We are not proving this because I don't know how to do it. I will just prove a fragment of this statement. So in order to do this, we understood we need semantics, so we need to briefly recall how models of dependent type theory look like. And in order to do this, we need a type theoretic language, a sort of type theoretic language of a display map category. I recall that a display map category is just a category with a distinguished family of arrows that we call the display maps. The idea is that we look at objects of such a structure as the variable context, and the display maps of codomain a context gamma as the types in that context, and the sections of a display map as I was mentioning before, as terms of the corresponding type. And finally, in order to re-index types and terms via morphisms of context, via substitutions, to obtain new types and new terms, we use the pullback operation that a display map category is endowed with. This is the idea at the basis of the main categorical ways that we have in the literature to phrase models of dependent type theory. According to this language, according to this translation, we can explicitly say when a display map category C is or is not a model of a type constructor. For instance, let us consider axiomatic identity types, where you have a formation rule, an introduction rule, an elimination rule, and a computation axiom. Thanks to the language that we have just seen, a display map category will be a model of these rules when you have, I call it a choice function, for each of these 4 rules that maps the interpretation of the premises into the interpretation of the conclusions. So we'll have in a display map category a function that for the interpretation of every type A produces the interpretation of this type, x equals x prime, as a display map. So the idea is that types will be interpreted as display maps and terms as sections. Then I will have a choice function that for a display map interpreting a type A will output a section interpreting R, and similarly for the terms J and H. To the interpretation of every instantiation of this data, you need a function that produces, that gives back a section interpreting J and a section interpreting H. If you follow this recipe to define what it means to be a model of these axiomatic identity types, you obtain this. So this slide is not meant to be read, it's just meant to show how intricate, how complicated, and how tedious the description of a model might be if we follow this syntactic description. And especially, it's very difficult sometimes to work with a model formulated in this way. However, sometimes we may be lucky and a type constructor may be characterized in terms of a categorical property of the family of display maps. I prepared an example, extensional identity types, which are axiomatic identity types where H here is a reflexivity and where you have this additional uniqueness principle. In this case, if you want a model of axiomatic identity types, what you want is a display map category with the following property, that whenever you give me a display map, its diagonal is itself isomorphic to a display map. So as you can see, in this case, these requirements are characterized by a single closure condition on the family of display maps. Again, that every display map has the diagonal isomorphic itself to a display map. And this proposition is an example of a theorem by Seeley, Hoffman, Maietti, Clérambault, and Gibier, telling us that the models of extensional type theory are the finitely complete categories. Okay, so what did we learn from this example? That a categorical description, a one-categorical description, clear and conceptually simple to state, exists for extensional type theory. However, this is not really the case for intensional type formers or axiomatic type formers, like this one that we have just seen without this uniqueness principle. In this case, there aren't obvious, I want to remark this, there aren't obvious one-dimensional categorical properties to characterize intensional inference rules. So in this case, a homotopy-theoretic description of models may be more useful. In this case, we sort of work with categorical structures, with display map categories, where we have also available a primitive family of weak equivalencies that we can use in order to phrase our intensional or axiomatic type formers. Because the idea is this: once you can talk about weak equivalencies, you can weaken the rules that characterize extensional type formers. You can weaken them in order to capture intensional type formers without collapsing them to their extensional version. And this is also related to the higher-categorical description of a model, where in place of using, where the idea is similar to the homotopy-theoretic description and to the categorical description. The idea is always the same, that we don't want this. We would like instead more categorical, more synthetic description to capture our models. But in the higher categorical description, instead of using a primitive notion of weak equivalence in your structure, you use you just work with a higher dimensional notion of a display map category, because also in that case, more conditions become available to characterize weak forms, so intensional forms of type formers. For instance, I want to briefly mention path categories, which are display map categories. Read vibration as display map. Maybe I should have written a display map here in place of vibration. So it is basically a display map category. So we use, again, vibrations to talk about the types, together with a family of weak equivalencies, such that some axioms that we are not going to read are satisfied. And the idea is that out of these axioms, you can prove that weak equivalencies and vibrations produce a weak version of a weak factorization system. So let us call it a very weak factorization system. And out of this very weak factorization system, together with Daniel Otten, we proved that these notions, these structures, these path categories are in fact the models of the display map categories, which happen to be models of axiomatic identity types. So this constitutes a homotopy-theoretic description of the models, the categorical models of axiomatic identity types. Okay. So I wanted to mention this result because out of path categories, which we understood to be the models of axiomatic identity types, we can actually extract a higher categorical description of models of axiomatic identity types. Especially, we can do it in the case where path categories are one-truncated, meaning that they believe that any two identity proofs between identity proofs are provably identical. Under this condition, we can define two-dimensional morphisms between parallel morphisms as homotopies, as the homotopies of your path category, which is a thing that you can define in a path category. And by doing this, you can prove that such a path category, so a one-truncated one, is actually enriched in groupoids. And additionally, the following conditions are satisfied. First of all, pullbacks of display maps of vibrations, which exist in a path category, after this enrichment, can be proven to be two-dimensional pullbacks. Secondly, vibrations are actually categorically speaking vibrations, because they are closed isovibrations, meaning that whenever P is a vibration or a display map, and you are given such a triangle that commutes up to a two-dimensional cell, you can find an arrow parallel to G such that the lower triangle commutes, so you can strictify this weakly commutative triangle up to lifting this homotopy to a homotopy between G and its transport, in such a way that once you post-compose back with P, you obtain the two cells you started from. And finally, every display map, every type, has an arrow object. Okay, so these conditions are very peculiar because, so what's the point? Because the point is that they are only two categorical, they are only higher categorical, two categorical. They are not homotopy-theoretic anymore, in the sense that they do not mention anymore the weak equivalencies of a path category. They only need the fact that path categories are 2-1 categories, that they are enriched in groupoids. Apart from that, they do not mention anymore the weak equivalencies. So what's the idea? The idea is that now we abstract out. We only consider a two-dimensional display map category, so a display map category with two-dimensional cells between the morphisms, okay? And we require these three conditions that we have just extracted from the notion of a path category, okay? And the point is that now these conditions, these two-dimensional conditions, are enough to rebuild, to recharacterize the semantics of axiomatic identity types. And I will briefly sketch how to do it. Basically, out of arrow objects, let us start from the first condition, that display maps are closed under pullbacks and that these pullbacks are two-dimensional pullbacks. This is just meant to being able to substitute into types and terms, as we usually do in display map categories in CWFs. The third condition, that you have arrow object, is meant that you have arrow objects for types, is meant to interpret identity types, but identity types that only admit a pseudo-elimination term, so not actually a section of the appropriate display map. Namely, when you try to build J, the elimination of the identity types, you cannot immediately build it as a section of a display map, but only as a section up to a two-dimensional cell, a pseudo-section. However, now we can use the axiom 2, that every type is a cloven isofibration, to strictify this pseudo-elimination term. So out of the axiom 2, we can strictify pseudo-elimination principles in change of producing, as I was saying, an additional two-dimensional cell here, which will be the interpretation of the computation axiom. So this is how you validate the J rule for identity types with the computation axioms. So with the computation axiom, so axiomatic identity types. Now, I do not have time to delve into the details. We can do it later during the question time if you are interested. But the idea is that the reason why you have computation axioms but not computation rules, so the reason why computation axioms do not hold on the laws, is that cloven isofibrations are not necessarily normal. From a path category, you can only prove that fibrations, that types in context, are cloven isofibrations, but you do not have the normality condition, namely the condition that tells you that if here I have the identity true cell, then the true cell that I obtain here is itself the identity. I do not have this condition in general, and this is exactly the reason why these cloven isofibrations are not necessarily. This is exactly the condition why you do not have the computation rule for the J principle necessarily validated. So the reason why these display map categories are models of axiomatic identity types and not in general of intensional identity types. Okay, so however, if you do have this condition, if you do have the normality condition, then this computation axiom becomes a computation rule and you validate intensional identity types. So we proved the following two things, that display map to categories are models of axiomatic identity types and one truncation. And I also sort of told you the idea why among these models of axiomatic identity types, the ones that are actually models of intensional identity types are precisely those whose Cloven isofibration structure over types is normal. Okay, so we have I make a consideration over these results. We have a categorical description of models of axiomatic identity types and intensional identity types, where we know concretely what's the difference between models of axiomatic identity types and models of intensional identity types. We have a way to distinguish between these two families of models that we can work with. We can work with this concretely because we know that the only difference is the isofibration structure over types. For axiomatic identity types, it is just Cloven, while for intensional identity types, for models of intensional identity types, it is normal. So this provides us with a structure to strictify models of axiomatic identity types, to strictify them into models of intensional identity types. So I will briefly recall what I said at the very beginning, that to prove that one truncated ITT is conservative over one truncated ATT, Hoffman's approach would be the following, showing that from the latter, we can build a model M of the former, so of ITT, such that the interpretation of ATT into M is surjective over terms. So the point is building M. And to build M, so to strictify models of ATT in order to produce models of ITT, now we know how to do it. We only know that given a contextual model of ATT, phrased as a contextual display map to category, we have to build an equivalent one whose types Cloven isofibration structure is not just Cloven, but it is also normal. So this is what we have to do, to find a way of strictifying the Cloven isofibration structure of the display maps of a model of ATT. But we need to be very careful because we need to do it in such a way that we do not destroy the CWF, the category with families structure of a display map to category. I didn't mention it, but these conditions are subject to many coherence conditions, stability under reindexing and stuff like that we usually have in type theory. So when we strictify the Cloven isofibration structure into a normal one, we need to do it in such a way that we maintain this coherence structure, this type theoretic structure. So we need to reobtain a CWF at the end, a category with families. In order to do it, so we just need other 2, maybe 3 minutes, if that is fine. To do this, we do as follows. Suppose that you are given a display map, so a type in context gamma. Then you build the following context. And you consider this arrow, which is essentially the projection on the second component. And what you do is you reindex your type, your display map, via this substitution in order to obtain this weird context. And the idea is that now we stipulate. So what would I like to do? I would like to replace this display map, which is a Cloven isofibration, with a new display map, which is normal as an isofibration. And I choose this composition, the composition of these red arrows, as my new display map. So I stipulate that the new display maps in the model that I want to build are the ones of this form, the ones like such a composition, whenever I'm given a display map. And you can also prove that this new display map, which I call overline A, is actually homotopy equivalent to the display map that you start from. And this will provide, in the end, the fullness condition that we need for the interpretation into the model that we are building. So I wanted to briefly mention syntactically what this means, and then I will be done. Essentially, whenever you're given a type in context gamma, what we are doing with this weird context, with this weird object, is actually the interpretation of the following context. So in the context gamma, now I will build my new type as follows. It consists of new variables for the type gamma, an identity proof, or maybe I should say an array of identity proofs from gamma to gamma prime, together with a term x of A over the fiber gamma prime. I stipulate that this new context is a new type, so a new display map in the model that I'm building. This may seem a bit exotic, but actually I want to remark that this is just Benabou construction to turn cloven fibrations into split fibrations. We all know about this. If you have a cloven fibration, we know that to build a split fibration, we just need to do the following thing. We stipulated that a new object, a new predicate over gamma is an arrow from gamma to some gamma prime, together with a predicate over gamma prime according to the fibration that you started from. In this way, we know that you build a split fibration which is equivalent to the cloven fibration that you started from. This is exactly what we are doing here. We are just internalizing this construction in a display map to category. So in this way, you actually build a new display map which is a cloven, which is again endowed with a cloven isofibration structure, but this time, this cloven isofibration structure is normal. Because now, if you have a lifting property, you have a very natural way to re-index G via pi, okay, in a very natural way, which happens to be to produce a normal cleavage for this isofibration structure. Okay, so this is the point of the proof, that out of a display map to category, restricting to context of this form, so the context that you can build using Benabou construction, you do obtain a new display map to category whose display maps are normal as isofibrations. And this constitutes a proof that of what we were saying at the beginning, using Hoffman's argument, that one truncated ITT is conservative over one truncated ATT. Okay, this is what I wanted to say. Thanks for listening to this talk.
Thank you very much, Matteo. We have our first round of silent applause, and now we move to question time. So do we have questions? If you do, please ask it. So while people are thinking, I have some questions, so maybe I start. So I have three, so maybe, sorry, someone spoke? Okay, so my first question is, so you're doing this for a very specific intentional type constructors, and we know that we have other intentional type constructors given an extensional type constructor. How much your approach could generalize to other intentional type constructors?
Thank you for the question, Ivan. As usual, when I do this kind of talks, I only focus on one type former, identity types. But I believe this argument can be extended to a wide class of intensional type formers and their axiomatic version. For instance, I checked that well, the empty type, the unit type, sigma types, and pi types are preserved by this model construction. So the structure adapts to a type theory with these type formers, at least.
This is very cool. And I have another question. This is a bit more provocatory. To some extent, we know what is an extensional type constructor. We have a definition. People can disagree, that's okay, but we can have candidate definitions. Do we have a definition of intensional type constructor, in your opinion?
The one that I use is just extensional type formers without the eta rule, so without the so-called uniqueness principle, with the effect that universal properties turn into weak universal properties with a choice of the arrow whose existence is required by the weak universal property.
Okay.
I use that one at least. While the axiomatic is when when the computation rule is weakened to the computation axiom.
Okay, thank you. There are some questions from other people, so maybe Jacopo, do you want to ask your question?
Yeah, thank you. Thanks, Matteo, for the talk. So I was wondering why you're using the splitting of vibrations, because if you start with any cleavage, you can actually turn the cleavage itself without changing the underlying vibration into a normal cleavage, not a split one, but a normal one. And maybe this construction can be done like formally as well in your setting. Have you checked that?
Thank you for your question, Jacopo. So the first approach would be the one you mentioned. You start from a cloven vibration and you just redefine the cleaving by saying, okay, the cleaving remains the same except when it acts over the identity. When it acts over the identity, I redefine it as the identity.
It doesn't quite work like that, but yeah.
Okay, there's another construction, more natural construction to turn it into a normal.
Yeah, somehow you need to post-compose and pre-compose with the with the proof of the reflexivity.
Thank you, Jacopo. I didn't know about this construction. Now I would like to check it. So the reason why I used the one I mentioned in this talk is just that it seemed the right way to do everything without breaking the CWF structure. But now that I know that there's another construction for just turning cloven vibrations into normal ones in a natural way, now I would also like to check if it works as well. So thank you for this. I will check.
You're welcome.
We have time for, I think, at least one other question, depending if it's short or long. Okay, if there are no more questions, then we thank the speaker one last time. Thank you very much, Matteo. Really nice talk. I really liked it.